like maybe I could get a little trim here. Jenny, Gianna, you were where you were sitting. We were doing some multiplying and factoring of trig functions, and then also some finding the errors in reducing rational expressions. Today we are going to start chapter 5. The first half of chapter 5 deals with simplifying trigonometric expressions and verifying trigonometric expressions. Essentially, they're the same thing, except when you verify, you know what the answer is, and when you simplify, you don't know what the answer is, which I'll show you the difference between the two. We will spend this week and a good bit of like the first half of next week, kind of just working through these problems. You can kind of assume that we will have 3 days for section 5.1 and like 3 days for section 5.2. I will say that the test on this is a 2-day test. I initially gave it as 1 day, and then I didn't have anybody ever finish it. So I broke it into 2 separate days. So it's not like a midterm, it's still 50 points. But it is a 2-day test. So there'll be part 1 with some problems and then part 2. So that'll be coming up closer to the end of next week. So it's just kind of looking ahead in advance. The second half of this chapter deals with solving trig equations and then using trig formulas. This is the last chapter that we will do with trig. So when we're done with chapter 5, we'll go back and do pre-calculus. And that's where we're going to do like partial fraction decomposition, something called Gaussian elimination. We will be looking at parametric equations, like all total new pre-calc concepts, because we need to build ourselves into calculus at this point. So thinking ahead for the next 3 months of the school year, we got 3 months left. The marking period has 3 weeks left in it. So even though today's the first day of school, again, for like the 15th time this year. The band was nice. Was the band still playing when you guys came in? No. Oh, sorry, Jenny, you missed it. It was nice. I got to hear it like probably 5 different times because I came early and they were playing from 6:45, maybe to like 7:10-ish. You might have just missed it. Yeah. So we are going to start in the chapter 5 packet if you want to pull that out. And just kind of talk about what to expect for chapter 5, which I kind of gave you a little summary. So this is the first page, which actually I guess is page 5. On page 3, you will see that here are the fundamental trig identities. I asked you to fill them out separately on a separate sheet. They're also on here. I strongly suggest you splitting your screen and either taking a screen capturing this and then pulling it up and splitting it on the side of your screen so you have it to look at. Or if you filled out the study sheet that I had attached to Friday's assignment, taking a screenshot of that and pulling it up and putting it on the side. I suggest you keeping these identities on the side of your screen because you're going to visually want to look at them until you get used to using the identities and the expressions that we work with. So going to page 5, just kind of talking about the difference between an expression and an equation. So a trig expression uses trig functions and operations. Operations, adding, subtracting, multiplying, dividing. So think of an algebraic expression, x squared y minus 3x squared y plus 2x minus 5y, something like that. So we're going to have trig functions and operations. So a trig expression might say the cosine of x times the secant of x, maybe times the tangent of x. That's an expression. So I have trig functions. The operation in this case is multiplication. Our goal will be to simplify the expression. And simplify means break something down as far as it can go, maybe to a single quantity, maybe because I'm combining like terms. In our case, we're going to be using trig identities. The other part of an expression is that there is no equal sign. That's what makes something an expression. So here would be my trig expression, and that's what we're going to work with in section 5.1. We're going to work on that type of problem and try to simplify it in trig terms. So yes, there's going to be some algebra that we do, but we're also going to be using trig to work through it. So Jack, what makes an equation different than an expression? Yeah, an equation has an equal sign. And of course, the goal of an equation is to solve. And in this case, we're going to be solving for the angle. So in trig, you solve for the angle. In algebra, you solve for x. So a trig equation might say the sine of x plus 2 equals, I don't know, maybe a 1. It has an equal sign, and we're going to solve for the angle. Well, in this case, the angle is x, but we will be solving for the angle, and that would be section 5.3. So an equal sign, we are going to be solving that equation for the angle and finding specific values for the angle. The last one is the identity, and the identity is what we're going to use to help us do the above two pieces, whether it's an expression or an equation. An identity is a property. Of our trig functions. A property holds true for all values of the angle. So a property might be sine squared plus cosine squared equals 1. That is the Pythagorean identity that probably gets used the most frequently. This identity holds true for any value of theta, for any angle. So I take the sine squared of an angle plus the cosine squared of an angle, it's equal to 1. And I can choose any angle that I want, and that identity will hold true. So we are going to kind of start in with section 5.1. And today we're going to work on simplifying fundamental trig identities. The first example is a more numerical example, and then the other ones kind of deal with expressions. So you can see number 2 looks similar to the problem that I gave you as an example of an expression. But we're going to first look at the information that's given here. It says use the fundamental identities to find sine and tangent. Given that the secant is equal to -3/2 and the tangent is bigger than 0. So we want to try and find the sine and the tangent using the fundamental trig identities. So that's key there. We want to try and use those identities. If you have secant, what other function can you find immediately without doing any work? Peter? Cosine. So anytime you have secant, secant is connected with the cosine because they are reciprocal functions. So if I know the secant, I can flip that around and say we really also know the cosine. Sometimes it's easier to think in terms of cosine than it is in terms of secant. So we have the fact that the cosine is -2/3 and the tangent is greater than 0. What quadrant would our angle be located in if the tangent is positive and the cosine is negative? So think about those 4 quadrants. We're not drawing a triangle, but where is the tangent positive? Let's start with that question. Kaden, where's tangent greater than 0? Between 1, 2, 3, and 4. Well, every function is positive in the first, so we know tangent is positive here. Where else is tangent positive? In the third. So tangent is positive in the first and tangent is positive in the third. Cosine is negative also in the third. So our angle is going to be located in quadrant 3. So when you go to think about your solutions, you have to remember that when you're finding the solutions, the angle is located in the third quadrant. So that's going to kind of remind us whether I have a positive or a negative answer. All right, so we're asked to find the sine and the tangent. And we know the cosine is negative 2/3. So think about using your identities. Oop. So here are mine, trying to squish them on the side here. If I know the cosine and we need to find the sine using some identities, how can I find the sine if I know the cosine is negative 2/3? Peter? So we can't do that because that's not an identity, that's part of a triangle. So yes, that's what I would do, except we have to use these identities to help us find it. So we're not drawing a triangle, we're not thinking opposite and adjacent, opposite and hypotenuse, adjacent over opposite, any of those things. We need to use one of these identities. Is there an identity that contains cosine but also sine? Because our goal is to find sine. Peter, you're going to try again?
Yeah, it would be sine of pi/2 minus x equal to cosine.
Oh, I see, under there. Unfortunately, no, because we don't know the angle. So, but yes. Yes, there you go. So it would be the Pythagorean identity, third time's a charm, right? So we are going to look at this Pythagorean identity where it says sine squared plus cosine squared equals 1. That's an identity that contains both sine and cosine. And if I want to find the sine and I know cosine, I should be able to plug a value into the identity. So I'm taking the sine squared, and instead of theta, I'm going to make it x since x is in the information we have, plus cosine squared, and then that's equal to 1. So that's the identity we're going to use. We know cosine. When you know something, you can use substitution and replace cosine with its value. So we're going to keep the sine. We know the cosine is negative 2/3. Well, the cosine is squared, so that means when I replace negative 2/3 in for cosine, it needs to be squared, and then it's equal to 1. So now we're going to treat this as an equation. I said there's algebra involved. We're going to solve this for x. Well, actually, we're solving it for the sine of x. So Jenny, if you square a fraction, what do you get when you square a fraction? Yes, you get 4/9. Continuing to solve, we want to get the sine squared by itself. So we would subtract 4/9 to the other side so that this 4/9 goes away. So now I have sine squared. 1 is really 9/9 minus 4/9 makes 5/9. Hannah, how would you get the sine by itself? Right now it says sine squared. So how, if it just said x squared, how would you get x by itself? So how do you think we're going to get sine by itself? Take the square root. So the operation in algebra is the same operation in trig. We're going to take the square root of both sides. Now, when you take the square root, just like Jenny said, you square both terms, you square root the numerator, you square root the denominator. So now I have the sign. The square root of 5 stays as the square root of 5, but the square root of 9 becomes 3. Except that anytime you take a square root, because you're solving for x squared, you need to place a plus or minus in front. That plus or minus is important because if I go back to my original information, we said that the angle is going to be located in the third quadrant. Jack, when we're talking about sine, is sine positive or negative in the third quadrant? It's negative. So my answer for sine is negative root 5 over 3. That was way more work than what Peter wanted to do. But I told him he wasn't allowed to use a triangle because we're trying to approach it in a different way. Sometimes more work isn't what you want to do, but we also have to be able to think in multiple ways as well. So now we know the sine is negative root 5 over 3. So we have sine. But the other thing it asked us to find was tangent. So it says find the sine and the tangent. Using one of the identities, how can we find the tangent? So look at your identities. We know sine, we know cosine. Peter, how can we find tangent? Yeah, and that's probably one of the ones that you think about. We usually say sine or tangent is a y over x. Well, y is sine, x is cosine. So the tangent is sine over cosine. I should change that theta. So that means my sine is negative root 5 over 3. Cosine is negative 2 over 3. When you're dividing fractions, what happens with the denominator if they're the same? They cancel out. So my fractions cancel. On the top is negative root 5. On the bottom is negative 2. If they're both negative, that becomes positive root 5 over 2. So the tangent is positive root 5 over 2. It's positive because my angle's in the third quadrant, and it works out that way as well because I have a negative value divided by a negative value, which makes that positive. Questions? So again, it's a different way of thinking about finding values for trig functions. Yes, a triangle is easier, but this whole chapter deals with identities and doesn't rely on triangles very much. So SOHCAHTOA is kind of like a thing of the past. We're now going to look at these identities. Any questions on that first problem? All right. So looking at example 2, it says transform the following expression into the value of 1. So they're telling us that eventually it's going to be equal to the number 1. We're going to try and use identities to simplify it or transform it to become the value of 1. We have the sine times the secant times the cotangent. And again, you want to look at those identities and try and think about which identity you can use to replace a function in your expression. And I would say keep sine because sine is one of the main trig functions. But let's look at secant. Gianna, what can we change secant into? You're right with 1 over. 1 over what? 1 over cosine. So we can change the secant to be 1 over cosine. Substitution says I can take out a function and replace it with whatever it's equivalent to. Cole, let's now look at cotangent. What can we change cotangent to, Cole? We can make it 1 over tangent. What else can we change it to? We can change it to cosine over sine. So instead of making it 1 over tangent, if I already have a sine and then something else with a cosine, let's change it to have just those two functions in the problem. So now I have sine, which I'm going to just place over 1 to make it a fraction. And then we have 1 over cosine, and then we have sine over cosine. Joe, what happens with these expressions that are being multiplied? Yeah. So when you're multiplying expressions, if something is the same in the numerator, with something anywhere in the denominator, it cancels, even though they're not next to each other. That's the commutative property of multiplication. So they cancel, and he said you're just left with the value of 1. So that is a trig expression simplifying to the value of 1 using identities. A rule of thumb would be to try and change terms to sine and cosine. That's a way to start. Whatever function you're given, can you change it to become a sine or a cosine? If you do that, then usually something ends up canceling from the problem. Questions on that first problem? All right, let's look at example 3. There are 2 different ones in here. This one says simplify the following expression. We have the sine times the cosine squared minus the sine. So thinking about what we did on Friday. Jack, what do you notice about those 2 expressions or 2 terms here? Sine, cosine squared minus sine. They both have sine. And usually if 2 terms have something in common, what do you do with it? You factor it out. So we're going to use that algebraic method. Let's factor out that sine. So Jack, when you factor out the sine, what do you get? Hey, you get cosine squared minus 1. So that's factoring. Now, yes, this cosine squared minus 1 could be factored further because it's a difference of 2 squares. However, our goal is to simplify this. We're going to try and break it down to its smallest possible value. So instead of factoring this further, we're going to now see if we can use an identity. So we did an algebra step. Is there an identity that we can possibly use to help us simplify this? If you look at your list, the Pythagorean identities are the only identities that are squared. And right now we have cosine squared minus 1. And in that list, I have sine squared plus cosine squared equals 1. That's the identity. Is there a way to manipulate this identity so that it says cosine squared minus 1? Because I want to use substitution. And if I can change this identity so that it becomes cosine squared minus 1, then I can use substitution. So how could I take this and make it cosine squared minus 1? So think algebraically, Jack. Yeah, so let's take the sine squared x to the other side. So we're going to subtract sine squared. And we're going to subtract 1. So we're going to do a little rearranging. So now my identity says cosine squared x minus 1 is equal to negative sine squared. An identity can be rearranged. It's the same identity, we just flipped some terms. So in my expression, we have the cosine squared x minus 1. In my identity, it's equal to negative sine squared. Substitution says you can replace an expression with whatever it's equal to. So instead of keeping the cosine squared x minus 1, we're going to replace it with the identity that it is equal to, and that is negative sine squared. So down here, this is like a little bit of scratch work. So this is us, come on, pen, showing how the identity is going to work. And I missed my x. There we go. So Jack, if I have sine times negative sine squared, what would that become? Negative sine cubed. Simplifying usually means break it down to a single term. I now have one function, and it's just sine. I started with two separate terms in my expression. By factoring and then using an identity, we've simplified it down to one term. Most times, that's going to be your goal. Can you simplify it down to one term or one number? So negative sine cubed would be our simplified expression. Questions? All right, let's try 3b. It looks very similar. We have a plus sign. We have sine times cotangent times cosine. Is there anything that we can factor? Unfortunately, there's not any factoring because there's nothing in common between the first and the second. So I can't use that method. Is there anything you can change? So those will be questions to ask yourself. Can I factor something, or can I change one of these functions? So we have a sine, we have a cotangent, and then we have a cosine. Is there something that can be changed? Peter? Yeah, that's probably a really good idea. Let's rewrite the cotangent, because I have a sine and I have a cosine, and I can change cotangent to also have those terms in it. So we have sine. Cotangent becomes cosine over sine. And then there's still a cosine right next to it. I'm just going to place that cosine over 1. Notice the angle changed to be a T. You will see various angles being used. All right, so this one's a little different. Each one of them have been slightly different than the one before. These two back here are still being multiplied. So we have the sine. We have to do the multiplication. So cosine times cosine, sine times 1. We need to perform the multiplication. So Kaden, cosine times cosine makes cosine squared. Remember, the squared goes next to the cosine, and then on the bottom is sine. I'm going to make this first sign a fraction as well. Just put my plus sign in the middle. So now I have sine over 1 plus cosine squared over sine. When you have two fractions and you're trying to add them together, Parker, what do you have to have in order to add fractions together? The same denominator. So Parker, what do you think this first denominator needs to be? It has to be a sine. So our goal is to add these two fractions together. That's what a plus sign means. I need to add. In order to add, we need to have a common denominator. Well, if the one on the right has a sign, the one on the left also needs a sign, which means I need to multiply the 1 by sine, and I need to multiply the top by sine. Remember, with a fraction, whatever you do to the bottom, you've got to do the same thing to the top. So Parker, on the top, we have sine times sine, and that becomes sine squared. So the whole goal of a common denominator is so that you can add the numerator together. Don't cancel anything. You just got a common denominator. This plus sign means I can now add the top. So if we add the top together, we have sine squared plus cosine squared all over the denominator, which is just a sine. So regular rules apply. If you're adding fractions, you add the numerator and you keep the common denominator. So we started first by using an identity, and then we did some algebra. And now we're at this step here where we have sine squared plus cosine squared. What can we do with sine squared plus cosine squared? Cool? We can just change it to 1 because my identity for the Pythagorean identity says sine squared plus cosine squared is equal to 1. And again, that's substitution. So you're going to take out sine squared plus cosine squared. We're replacing it with the identity, which just says it's equal to 1. The denominator didn't change. So finally, Cole, we're left with 1 over sine t. What is that the same as with an identity? Yep, you're right. It is equal to the cosecant. So right over here, 1 over the sine is equal to the cosecant. If you can simplify it to be one term, then the expression has been completely simplified. Now, in terms of difficulty, that one was way more difficult than the other two that we did. It involved algebra and it involved multiple identities. So we used 3 identities, and we also used a couple of different algebraic concepts. Question. Anything you want re-explained? So I would like you to go to the top of the next page. It says to factor, and we did this on Friday. See if you can factor this expression. So 2 of them here. Try and factor those 2 expressions. So we have secant theta minus 1. Think about how does that factor? It's just asking you to factor. Doesn't say to simplify, it just says to factor. Brenna, how would you factor secant squared minus 1? Nice. So this is just like having x squared minus 1. X minus 1, x plus 1. So if you'd rather think about it in terms of x, kind of think. It really is treated like an x. We factor it the same way. Secant minus 1, secant plus 1. The one next to it, this one's a little different. We have cosecant squared minus cotangent minus 3. For us to be able to factor, we need to have all x's. I have to have the same function in order to factor. Right now we have cosecant squared minus cotangent minus 3. So I can't factor quite yet because that cosecant squared doesn't match a cotangent in the middle. So if I can't factor, we have to try and use an identity. So if you look at that Pythagorean identities, I have a cosecant squared. Hannah, one of those identities involve a cosecant squared. What does it say cosecant squared is equal to? Yeah, cotangent squared plus 1. So I can replace cosecant squared with cotangent squared plus 1. But then I still have a minus cotangent, and we still have a minus 3. We just replaced the first function with its identity. Hannah, what do you think you would do next to them? Yeah, we're going to do some grouping here. But before we get to that, let's add the two numbers together, because there's a plus 1 and a minus 3. So now I have cotangent squared minus cotangent, and now it's minus 2. So we're still going to factor it, but you can't factor it until you have the same function in the equation or in the expression. So Hannah, we're dealing with a minus 2. What two numbers multiply together to be negative 2, but add to be negative 1? Negative 2 and 1. So coefficient is a 1 in front. This is the shortcut factoring. Cotangent x minus 2, cotangent x plus 1. So take your two factors, use the function that's in our expression, it's cotangent, and then those two factors go in parentheses with our function. Questions? So there are two more problems down below, and we will start example 5 here. Example 5 says rewrite the following expression so that it is not in fractional form. And we have 1 over 1 plus the sign. So the goal is to make it not a fraction. We are going to use a concept that we used a lot in chapter 2 to make sure that the denominator didn't have i's in it. The denominator didn't have imaginary numbers. We're going to use the concept that we also used in chapter 2 so that our denominator didn't have radicals in it. So what could I multiply by? What did we multiply by when we were talking about imaginary numbers? What did we multiply by to rationalize the denominator?
1 minus sign.
Yeah, do you remember what that's called? Begins with a C. Anybody remember what that's called when you multiply by the opposite? The conjugate. So we're going to use the conjugate fact to help us reduce this expression. So we're going to multiply the bottom by 1 minus sign. But whatever I do to the bottom, I have to do to the top as well. So my top is 1 minus sign. And you're going to FOIL the bottom. So 1, and we'll finish this tomorrow, minus sign, plus sign, minus sign squared. So we'll stop there. Your homework, each problem is different. The more we practice these, the more comfortable you'll feel. But it's not a cookie cutter problem. So I can't just solve all of them the same way. They will be more challenging than others. So do the best that you can. Use those identities. Have a fantastic Monday. Everybody home, have a good day.